All right, so this is the last section in chapter 3. So your test is all in chapter 3. So 11 sections. So 3.11. Related rates. All right, so the title kind of explains it all. How is one rate related to another rate? A rate is something that is changing, right? So really, the most classic example, I guess you could say in a calculus class is always given, okay, you have an oil spill in the Gulf of Mexico or wherever. So it's bubbling up, right? So you're leaking so many gallons per minute, perhaps, per hour, per second, who knows? Okay, something like that. But it's a rate, right? Just that oil coming out of the pipe or wherever, right? It's coming to the surface. And when it gets to the surface, what happens? It spreads out, right? Spreads out in somewhat of a circular pattern, right? So we could say the area of that circle of the oil spill is constantly increasing as well, right? So how is the rate of change of the oil coming out of the pipe affecting the rate of change of the surface area on top of the water? So if you know one, you can figure out the other. So that's what related rates are. That's what we're going to do today. It's not really difficult. The only thing that's probably a little bit more difficult to think about is because they are word problems. It's implicit differentiation. That's what we've been doing already. So there's pretty much a recipe for these. And so every question, you're going to do the same thing. Step 1, step 2, step 3, step 4, answer the question. And there are very many classic calculus applications. Oil spill 1 is one. A ladder being pulled away from a wall. We'll look at that one. Sand coming off a conveyor belt and forming a cone. So we'll look at some of these and bore you to death today, all right? All right, so let's see. Let's do the oil example. Spreading oil. If the oil patch, if the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing? When the radius is 100 meters. So it's an instantaneous rate of change. So exactly when you get to 100 meters, you want to have a measurement, basically, measure that rate. It's kind of like the speed of a car, right? Remember, we had instantaneous velocity, those kinds of things, not average. Instantaneous, one particular point in time, hit the radar gun and speed, right? So we have the area, right? At some time t is what we're looking for, right? How fast is the area of the patch increasing? So pretty much you can assume it's going to be a circular nature, right? As long as the waves aren't really rough and stuff like that. Suppose it's just smooth, calm lake or somewhere. As it's coming up to the surface, it's going to expand as a circle. So you always going to want to find some kind of equation that you are familiar with, okay? Lots of these are areas or volumes or some of those kinds of things. So area of a circle, pi r squared, right? So this is pi. R is squared, but R is a function of time, right? The radius is changing at a rate of 30 meters per hour. So radius as a function of time, all squared. How fast? This is a rate that I'm looking for, right? I'm looking for the rate of change of the area. Rate of changes. Remember I said if you don't know what to do, always do it. Take derivative. That's the derivative of the area formula that we just came up with, right? So I'm gonna do a prime at t. And then look at this over here. This is some function r of t, right? Inside the other function. This chain rule stuff going on right here, right? So we're gonna have power rule 2 times the pi to the r of t to the 1 less power, and then we have to put in the derivative of that inside, which is r prime at t. So chain rule. So we're given that the radius is changing at a rate of 30 meters per hour, right? This is equal to r prime at t, right? Radius is changing. It's the rate of change of the radius. And the radius at some particular time is equal to 100 meters. So taking this rate of change of the area, I can plug in these numbers. 2 pi, r of t, 100, r prime of t. Let's put the meters there. R prime of t is 30 meters per hour. All right, so I'm gonna evaluate all this out with the calculator, get an approximate value, because you're not gonna go around saying, in this case, 3,000, 6,000 pi, right? 6,000 pi, what is that? About 18,850. Meters squared per hour. So the area is changing, roughly almost 19,000 meters squared every hour. Or just a radius changing at 30 meters per hour. So that radius is linear, the area is quadratic, right? All right, so that's a typical example of a related rate. So let's break it all down and list the steps that are involved. First step. So steps to solving related rate problems. Number one. always. First step in any word problem, read carefully. Reread it if you need to. Try to understand what's being asked, right? We need to decipher this sentence means this sentence means this. What are we looking for? Figure out what is the unknown. So draw a picture if you need to. Many of these pictures will be really helpful. Identify the given rates and those to be found. So we're always looking for some derivative, right? A rate of change. We will probably most likely also be given a rate of change. So identify those parts, okay? Number 2, find a formula that can relate the variables. So earlier we knew we were dealing with the circle, area of a circle, pi r squared, radius was involved, that was given to us. Yep, area goes with radius. That was one of the formulas. Third step, differentiate the formula. With respect to time, it's usually always to time is what we're looking for. Find t. Step 4, substitute known values. And solve for the desired rate, if that's what's being asked. Let's just put the unknown variable.
Set differentiate means found.
Find the derivative. And sometimes we might have to use implicit differentiation. Sometimes it's just straightforward, it's a chain rule, depends what the equation is that we're looking at, that's how related to the variable. Number 5, probably one of the most important ones, check that all units correct and solution is reasonable. So we would have did our calculations wrong and say we've got, okay, we're a radius of 30 meters per hour is just changing. And if I get an area that is changing at 2 feet per day, that doesn't make sense, right? Logically, if it's changing the radius is 30, it has to be a lot bigger than 30, right? When you look at the area as a whole picture, it just make sure your calculations somewhat make a little bit of sense. So let's do another one. Following these steps. If you blow up a balloon, and it's spherical in shape. Obviously, some balloons are not exactly perfectly round, right? But we're gonna say this one is, so make it easier, right? Because we know formulas of round things, right? Because most balloons, they come egg shaped, right? I don't know the equation of an egg shape, right? So we may know the equation of a sphere. Okay, so you blow up a balloon, spherical in shape with air, and the volume of the balloon is changing at a rate of 100 centimeters cubed per second. How fast is the radius increasing? When the diameter is 50 centimeters. So you can just think about this balloon that's getting bigger and bigger and bigger. So you pump it in lots and lots of air. Think about when it gets really big, even though you pump it in lots of air, the shape or size, the shape's still staying the same. But the size of the balloon probably is not increasing as big anymore, right? Because there's more volume in there than before. So starting off, that rate of change is probably going quick. Slows down, even though you might be still pumping in the same amount of air at that given rate, right? Eventually it pops, right? Maybe. All right, so first step, read the problem, right? Everybody understands what we're looking for, right? Draw a picture. We gotta draw a picture, of course. See, I like red balloons. There we go. Nice red balloon. Now let's color it in. You gotta realize this is art class too, right? You rather grade in art class or a grade in calculus? Usually there's mixed feelings about that. Like, see, I can't even color within the lines. I fail. I can't fail kindergarten. All right, so we got a balloon there with a air is going in at a rate of 100 centimeters per second. Cube per second. So this is right here. The volume is changing, right? At a rate of 100 centimeters cubed per second. So this is the derivative of volume. I'll use this notation for now. dV over dt, right? That's given. We're looking for the unknown. So what we're asked is the rate at which the radius is increasing, right? So this is the derivative of the radius with respect to time equals what? And we want to do this at a diameter equal to 50. All right, so our second step is to figure out what is a formula that relates volume and radius, right? Anybody know the volume of a sphere? Probably not right there at the top of your head, right? May have used it once or twice way a long time ago, and probably it's like get, you know, jump that, stay space or something else, right? But the volume of the sphere is equal to 4/3 times pi R cubed. Remember, cube talks about 3D square, 2D area, right? So volume is cubed. So sometimes you come across a formula that you're like, I have no idea what it is. Google it if it's in the homework, if they're not telling you right away. Okay, because sometimes they expect you to say, okay, what is the volume of a dodecahedron? Oh, a dodecahedron. See that shape on the back cabinet over there? Similar to that. Bunch of different shapes of either octagons, those kind of things. Think Epcot, those kinds of things. All right, so if it's something on the test, if it's not a well-known formula, you should know your circle formulas, right? Pi r squared. What's the area of a triangle? 1/2 base times height. Those you should know, but for some reason you don't know the formula, or you tell me, I know which formula it is. I need to find the area of a triangle, but I don't know what it is. I'll tell you. You gotta at least tell me that much. I'm not gonna say, okay, here's your formula. Use this one, right? You have to at least tell me which one it's gonna be. Pythagorean theorem, there's that one. If you have a picture and all of a sudden you got a right triangle that's being drawn, Pythagorean theorem, right? So, or the area of a triangle. So something straightforward would be on a test like that, to where you should know these well-known formulas. All right, so we got our formula. Now I'm going to take this formula and differentiate it. That's our third step. So I'm going to take the derivative with respect to time of the left side and the derivative with respect to time of the right side. Now again, that previous example, I used these as functions of t. I wrote it in its function notation. You can still do that, or you can now just use this notation. You can use prime marks, however you wish. I find this kind of notation is kind of easy because you're actually reading it. This is the derivative of, right here, the derivative of the volume with respect to time. Right? I'm trying to solve for the derivative of the radius with respect to time. So now let's just plug all this in right here. This is going to be dv over dt, right? The derivative of v, derivative of v. The derivative of all this mess here. Careful right here, though. Four-thirds, pi is not a variable, right? Pi is a constant. So we just use the power rule right here. 3 times all of this gives 3 times 4/3 pi to the r to the 3 minus 1 power is squared. And then it's respect to time, right? So t is not in here, so we need to tackle on the chain rule, the derivative of r with respect to time. These 3's cancel out. All right, now I replace everything that is known. dv dt, that's 100 centimeters cubed per second. You could put the units in the problem, or you can wait towards the end and get your units. Think about how is the radius changing. It's going to be, you'll see the units. The radius is linear. Right? Is equal to 4 pi when the radius is how big? Diameter is 50.
25.
Radius is 25. Times dr dt, we don't know. I think I may use a capital R at the top, but yeah, it doesn't matter. All right, so we got everything. This is 25 meters squared, right? All right, let's clean all this up. Four times 25 squared, 25 squared. We write it this way, maybe it might get a little bit deeper now. It's okay. 25 out squared is 625 meters squared dr/dt.
The unit you put there matter.
Mm-hmm.
The unit you put there is matter. Like
Meters?
yes,
Yeah, no, we have to do some versions on. Because we got centimeters and we got meters here.
yes. But you cannot assume that's a centimeter.
Oh, because it was 25. Oh, centimeters. You're right, centimeters. Good, that makes it even better. I was thinking meters. Centimeters. Everything's at centimeters. Good. So that's centimeters squared. All right, so now I got to divide everything by 4 pi 625 centimeters squared. Well, that cancels, and that has solved for dr over dt at a radius of 25 would be this rate. Notice these centimeters squares will cancel with the centimeters cubed. So we get a rate of centimeters per second, right? It makes sense, right? The radius is linear, right? It's a linear measure. So let's put this in the calculator. We got 100 divided by the 4 pi times 625. We'll put all that in parentheses. The denominator. And there is your answer, 0.0127. It's pretty good. So roughly a tenth of a hundredth of a centimeter, right? So it's not changing all that fast. I told you at the beginning, once you get to a large balloon, right, even though you pump it in the same amount or quantity of air at that rate, the entire balloon is probably not changing very, very much. Right? So that 100 centimeters cubed per second is being dispersed a lot, right, instead of in a small quantity. All right, so that was our fifth step. Make sure it makes sense. Yes, this does. Good. 50 centimeters. So like that, perhaps. All right, so there is your recipe. So draw a picture, identify what is given, what is unknown. Those are typically rates. Right? You're usually given some specific point, like at 50. So we're trying to find the radius at 50. Well, so the diameter was at 50 centimeters. So our radius is 25. So that once you differentiate your equation next, there's usually one thing that is unknown, and it's typically a rate. You can find it. All right, let's look at another one, a ladder sliding down a wall. See a 13-foot ladder. It is leaning against the vertical wall. You start pulling the foot of the ladder away from the wall. At a rate of 0.5 feet per second. So every second it's moving back half a foot. Every 2 seconds, 1 foot, right? How fast is the top of the ladder sliding down the wall? Very classic related rate problem. I could give you how to measure this rate at a specific point in time. When the foot of the ladder is 5 feet from the wall.
So the 13 feet at the beginning given is not useful. Right?
Yeah, it's useful. Watch with the picture we draw, you'll see why it's useful. Okay, so we have a wall. That is vertical, right? And put a ladder against this wall, right? This ladder is 13 foot long. That picture we're drawing. See. Right triangle, right? Huh. So that $1 million if it's the right triangle and sides are involved. Pythagorean theorem would probably be our equation, right? Especially over a right triangle. So hint, hint. All right, so let's see what's given. So if I say the horizontal, let's call that X, right? Let's call this Y. So these are the lengths of all the sides, right? So I don't know exactly how high the ladder is way up, right? I don't know if it's really, really almost vertical, very steep, or if it's really shallow, right? But I'm taking that ladder and pulling it back, right? A specific rate. So that's given. Is the rate of change of X, right? That's the horizontal rate that X is changing. That's my mouse. So the derivative of X with respect to time is equal to 0.5 feet per second. We're looking for the rate of change of the ladder coming down. So that's in the vertical direction, right? So we're looking for dy over dx. dt, that is. dy over dt is the rate of change of the ladder. Just say falling. So there is an equation that relates all three sides, right? So the equation is x squared plus y squared must be equal to 13. have the equation relating all the variables. Now I differentiate. The derivative with respect to time of x squared plus y squared. Got to put this 13 squared, right? All right, so keep in mind, this is always with respect to time of these variables, so the chain rule will apply, right? So this is for the derivative with respect to time of x squared is going to be 2x times dx dt. Same thing for the y, 2y times dy dt is equal to the derivative of 13 squared. That's 169. That's a constant derivative. Any constant is always 0, right? Feel like you want to be specific, you say derivative of the constant with respect to time. You put some d's and all that, but times 0 is still 0, right? All right, now we make our substitutions. So this was asked for when x is 5 feet, right? 2 times 5 times the rate of change that x is with respect to time. That was given as half a foot, so 0.5 feet per second. Plus 2 times y. Oh, I don't have y. Or do I? You have y. If we have, this hypotenuse is always 13, right? No matter how it's sliding, the hypotenuse is not changing. My basis could be changing, right? But at one point, we know that this is 5 feet, right? That's where we want to look at it. So I need to figure out this. So 5 squared plus y squared is 13 squared. Y squared is 169 minus 25 is 144. Technically, y is plus or minus negative 12, plus or minus 12, but looking at the distance is the positive 12, right? So y is 12 when x is 5. So I solve this equation for dy dt, and that's going to give me the rate of change that the ladder is sliding down. So that's 10 times 0.5 makes 5 feet per second. I can take off all the units right now. It's probably easier just not even worry about them. We know it's going to also be changing at feet per second, right? Let's just do that so it doesn't get too messy. That's just 5. This is 24. dy over dt is equal to 0. dy dt is equal to subtract the 5 and divide by 24, right? So negative 5/24 feet per second. If you want to express that as a decimal, you could do that as well. Negative 5 over 24. Why is it negative?
Mine's goes down.
It's going down, right? So the rate of change is going down. So the negative indicates the direction. So 5/24 is put that 24 0.21. So it's coming down not as fast as it's moving horizontally, right? All right, sand's falling off a conveyor belt. So you imagine that, right? Let's just draw a picture. Do that first and finish the problem. So we got our little conveyor belt going up. Sand. Like this. And it falls over. And it starts to form a pile. What shape is this pile? Cone. It's gonna be a cone, right? All right. So it falls off the conveyor belt onto the ground with a radius. I think there's a delay today. I need to shut this computer down one day. With a radius that is always 3 times its height. So basically the speed of the belt is determining that radius down here. Always 3 times its height. The sand is falling at a rate of 120 feet cubed per minute. How fast is the height of the sand pile changing? When it's 10 foot high. Exactly when it gets to 10 feet, measure that rate, you'll see what's happening. Now, think about it. Similar to that balloon problem. The higher, more sand that's being dispersed, the change in the height of the pile probably won't be changing much because all of that is now covering a lot more surface area to be dispersed upon, right? So the more and more, if I would say that, if I do it at 10 feet and then do it at 50 feet, I would assume that the rate of change of the height is going to be a lot less than the rate of change is at 10 feet. All right, so what's given? We have the rate
Falling rate.
of volume, right? So we have a volume right here. The derivative of volume with respect to time is given to be 120 feet cubed per minute. It's unknown what rate. How fast is the height? dH over dt. Right, so there is a formula that relates volume, height, radius, and all that kind of stuff. Volume of a cone. Probably don't remember. I don't remember. If anybody asked me off the street, I would say, oh, hey Siri, what's the volume of a cone? So that would be equal to, volume of a cone is equal to 1/3 pi r squared times its height. Not too bad of a formula, but it's just like I said, not many people just memorize all these volume formulas too often. All right, notice in here, in our formula, we have 3 variables, right? Feet is a variable. that can change, the radius can change, and height can change, right? So there's a little bit of a problem. Usually you just have one equation in terms of one variable, right? Makes it a lot easier. So we were given some other information in the problem. That the radius is always 3 times the height, right? So r is equal always to 3h. So now I can say, now if I put in r as 3h there, now I only have one variable to work with. That's kind of the variable I'm more interested in, right? Is because that's the question that's asking the rate of change of the height. I'm not concerned about the rate of change of the radius. So now I'm gonna have v is equal to 1/3 pi. R is now 3h squared times another h, and simplify all that. 1/3 pi times 9h cubed. 3 and the 9 cancels, so that's just 3 pi h cubed. Take this equation, volume in terms of just height only, and differentiate it with respect to time. To the left is the derivative of the volume with respect to time is equal to, all right, again, our variable in here is h, but we're differentiating with respect to t, chain rule. So this is 3 times 3 pi is 9 pi. Power rule applies. H squared times d h d t. Substitute. dv over dt was given to be, what's that, 120 feet cubed per minute is equal to 9 pi at a height of, we were saying at 10 feet, right? That's where we want to know the rate of change. So 10 feet squared. Squared on the outside. dH/dt. Divide everything by all of that mess right there, and you solve for dH/dt. Again, you probably just want to use a calculator for all of this to get up. 120 divided by 9 pi times 10, 90 pi. That would all come out to be equal to 0.042. This would be feet per second. Remember, feet is going to be a linear measure, right? And if you do all the cancellation of your units there, you'll see you'll get feet squared cancel feet cubed, given feet to the first. So how are we feeling about this? Easy? Boring? Repetitive?
You cover the unit?
What's that?
Are you gonna cover?
Not finished yet. No, I gotta do about 100 more examples if you want. No, not 100, but more. So I'll give you pretty much every type of example that you'll see in your homework too, and something very similar that would be on the test too. Okay, so you're going through your notes and you understand all these problems, and you can go to the homework and you can do those problems. When you see it on the test, it's be a walk in the park. All right, filming a rocket launch. You guys ever seen a rocket launch before? pretty cool. I actually got to witness one of the space shuttle launches. I don't remember which one it was. It wasn't one that blew up. You know, thank God I wasn't there. But we were in Cape Canaveral. We were in Disney World at one point, and we heard they were doing a launch. So I was like, oh, let's see if we can watch it. But anyway, we did it. And you park right miles away from the launch pad because if anything happens, you know, it's a hit you. But you could barely see the space shuttle way off in the distance or whatever. But you park right on the little coastline or whatever in the marshy area and stuff. And you just listen to the radio and they said, if anything happens, the best thing to do, jump in the water because you got fire falling from the sky. So you never know if you would get hit. It's like, okay, this is pretty serious. But everything went off perfectly. It was really cool and extremely loud. You wouldn't think something so far away would be that loud. It just it's fast, super fast. It's awesome. All right, so suppose a cameraman wants to film the launch. He sets his camera. 3,000 feet away from the launch pad. When the rocket reaches an altitude 4,000 feet, it is climbing at 600 feet per second. How fast does the angle of elevation have to change? At 4,000 feet to keep up with the rocket. You know, I probably could have just copied all these for you and just handed them out and you could have read them, right? I agree with that sometimes, and sometimes I don't agree because really writing things down, I don't know for you guys, but for me, it just reinforced everything. Like writing it, reading it, right? Just makes it stick. Yeah, your hand might be getting tired, but hopefully it's sinking into your brain exactly what's being asked, what's being given, those kind of things. All right, so we got a rocket, right? Space shuttle, a rocket. Let's see. Let's do a space shuttle. See if they don't have a space shuttle anymore, right? But you can look at them. Museums now. This. Of course, you got the other tanks, right? You got the, what's it called, the external fuel tank, and then two rocket boosters. That was a NASA nerd. Okay. All right, so at 4,000 feet right there, it's altitude. And we got a cameraman way over here, right? So he's got his camera, something like that. Sunny. Should I put that up a little bit further? Oh, look, we got a right triangle. Oh, go figure. Something probably gonna happen with right triangles again. We're looking at the angle of elevation. Remember, angle of elevation is from the horizon, the horizontal, looking up, right? Going up. So this is your angle of elevation right here. Let's call that theta. So that's what we're asked to find, right? That's our unknown. Let's go ahead and write that. The rate of change of the angle of elevation. That's derivative of theta with respect to time. All right, let's call this X, I guess, as a horizontal. We can call this side Y if we want, or let's, in better terms, I guess, for what's given, H. Let's do this H, I guess. We're told in the problem that the rate of change of the height at that 4,000 foot altitude is 600 feet per second, right? So that's dH, derivative of the height with respect to time, is equal to 600 feet per second. We know X specifically in this problem, its distance is 3,000. The height also is given right now, right? H is going to be equal to 4,000, right? All right, so now if I look at H, X, and theta, there is some equation relating all of those. True. H is opposite, X is adjacent with respect to theta. That's tangent, right? So tangent of theta, so here's our equation, is equal to H. Now, our H can change, right? We're just looking at it specifically at that. Will the X ever change? No, X is never changing, right? So this is fixed. This can change, obviously. The total's just when it gets to 4,000, it's just not floating in the air, right? It's going to keep moving. So this can change. So we're going to say our X value is 3,000. That's in the bottom, right? Opposite is H. I'm going to differentiate this. I'm going to rewrite this to where it makes it a little bit easier. This is 1 over 3,000, right? Times H. Make it as a coefficient in front of the H, right? It's easier to see than if I take the derivative of that. Just the power rule, right? Makes it a lot easier. Because if you're looking at it, H divided by 3,000, to take the derivative of that, most people are thinking, oh, that's going to be the quotient rule because I got a quotient. But yes and no, it can be done. It's just always try to find a more efficient route because there's H only in the numerator, not everywhere. So if it was everywhere, then you probably have to use quotient rule. All right, so now we take derivative of both sides. So the derivative with respect to time of the tangent of theta is equal to the derivative with respect to time of 1 over 3,000 H. what's the derivative of the tangent? Secant squared of theta, right? But we're doing with respect to time, so we gotta tack on the chain rule. D theta over dt. Over here, derivative of 1/3000th h. That is just 1/3000 times dh dt. Substitute. Like substitute now or substitute later, just isolate the equation for dh dt. That's what we're looking for, right? So whatever you wish. All right, so I have let's see. In our picture, this point in time, height is 4,000. This is 3,000. Don't I know this value here?
Yes.
What's the hypotenuse? Pythagorean theorem.
Um,
3,000 squared plus 4,000 squared is equal to something divided by square root it, whatever. This is 5,000. That's a 345 triangle, right? All right, so I need to figure out what is the secant. Secant of theta is what? This is x, this is say y, and say this is r. Secant's reciprocal was cosine. Cosine is x over r, so this is r over x. That's 5,000 over 3,000. That's 5/3. So now we can put that value in this place, 5/3 all squared. Times d theta dt. No. It's equal to 1/3000 times dh over dt. The height is changing with respect to time at a rate of 600 feet per second. A little math magic, isolates d theta dt. Let's see, I'll entertain you. On the right side, we got 6,000 divided by 600 divided by 3,000. All that's going to be divided by 25 ninths. It's going to give you 0.072. Now this is radians per second. I'm going to tell you everything when we do in calculus, your angle values are always going to be a radian measure because of the units as radians is a ratio, right? Ratio with the arc length and the radius. You know, saying that's equal to 1. So this is going to give you 0.072 radians per second. In real world, does that make any sense to anybody? Do you know what 0.072 radians look like? Probably put it in degrees, it'll make a little bit more sense. So to change radians to degrees,
so 180.
0.072 times 180 over pi. So 0.072 times 180 divided by pi. About 4.125 radian degrees, 4.13 is good enough. Degrees per second. So every second, change your camera angle about 4 degrees, 4 degrees, 4 degrees, and it'll keep up. And probably, like I said, the higher it goes up, you don't have to keep increasing at 4 degrees. That rate of change is probably going to start decreasing because the distance is further and further away. So you don't have to make that angle adjustment as vertical. Let's see. One more. Okay, so normally let you guys like I'll work an example and you guys try to work one and work it all together and stuff like this. Really, these kind of problems is I can just give you as many examples as necessary, and then you have to go out and just figure if you could do it on your own. So try to give you as much as possible today as well. I'm not waiting 15, 20 minutes for you guys. Work. That's to be after spring break. So, all right, so converging airplanes. They're not going to collide. I have to get a flight next week. I don't know. All right, two planes, let's call them A and B. A is going due west at 120 miles an hour. And B is going due north at 150 miles per hour. How fast is the distance between the two planes? Changing. When they are, when A is 180 miles away from the airport and B is 225 miles. Converging means coming together, right, to a central location, the airport. A is going due west, B is going due north, so they're getting closer and closer and closer together, right? So let's draw that picture. So we got the airport, plane A is heading due west towards the airport. Plane B is going due north towards the airport. And we want to know what is the distance between the two planes? How are they changing? So we have some values right now. A is 180 miles from the airport. B is 225 miles from the airport. Forms a right angle. Oh, go figure again. Right now, at these specific points in time, we can calculate exactly how far this distance is, right? Pythagorean theorem. So let's call this, this is horizontal, let's call it y, x. Vertical, let's call it y. The diagonal, we call anything you want. X, y, how about z? So z is equal to the square root of 180 squared plus 225 squared, which is, let's see what this calculates out to. I think it's a nice value, 180 plus 225 squared. Take square root of that. About 288. Okay, so it's not exact, but that's close enough. Really talking about tenths of a mile. That's irrelevant, especially when they're moving. All right, so we also have a formula that relates all three of these sides, right? Pythagorean theorem. Z squared is equal to, in this case, x squared plus y squared. I will differentiate both sides with respect to the time t. Again, all of these with respect to the variable t, which there's no variable t in there, so it's a chain rule. This would be 2z dz dt, 2x dx dt, plus 2y dy dt. We're given some rate of changes for x and for y, right? We're trying to figure out the rate of change for z. When z is 288, so 2 times 288, dz dt is going to be our unknown. 2 times the x value for that particular value is 180. The rate of change that plane A is doing, what's it going? 120 miles per hour. Two times the y value is 225. The rate of change of plane B is 150 miles per hour. So if you take all these values here, the right side, and then we'll divide by 2 times 288, that will solve for dz dt, right? So that's 360 times 120. Plus 225, that's 450 plus times 150. So that's the right side divided by 2 times 288. It is 192 miles. All right, so obviously you can tell from this picture, as they're getting closer and closer to the airport, the hypotenuse has to be shrinking, right? So if you would do this and say, okay, if they are now at 100 miles from the airport for A and 150 for B, you should have that rate smaller and smaller and smaller, right? All right, questions? That is related rates.
That was not minus.
Is what?
No, just in common sense, if the distance decrease, so it should be minus negative, right?
Yeah, yeah. What we did wrong. I guess negative. Is there a negative somewhere in here? Let's see. You could think about, okay, their rate of change. Okay, so due west at 120 miles an hour, so they're getting closer and closer to their rate of change. Got to slow down, right? So you got to start decreasing to get to the airport, right?
Probably.
I guess you could start increasing. I mean, that's not.
Oh, okay, I got it. That maybe
You're coming to get to the airport, so the rate of change is going to be changing. Just wondering. Let's see.
or maybe they can cross each other.
Yeah, they
before
could cross
you
each other. One could be at a higher altitude, hopefully, right? Changing.
Because they're going the same speed and they're getting closer to each other, the rate at which they're getting closer to each other will increase, right?
The diagonal
Yeah,
is going to be getting,
smaller, faster.
yes.
Yeah.
Yes,
So that's why it's speeding up.
yes, yes.
Wait, you say that
As this plane's going this way, this plane's going this way, this is changing faster as they're getting closer to the earth. The rate of changes.
Think about it like the Pythagorean theorem.
The distance is getting smaller and smaller
Yeah.
and smaller. But the rate that the distance is getting smaller is getting larger quicker. It's kind of hard to think about it. If you would put in another scenario, change your distances and calculate the rate then. Instead of them being at their 180 and 225, make them smaller. Put it at 100 and 150. You'll have a rate that is more than 92 miles per hour. It's kind of the same concept with that balloon just now. The bigger the balloon gets, right, the rate of change of the radius perhaps is not changing at all. But it is changing,
So
but very slightly, right? Although you're pumping in more and more air into it, it's covering, it's dispersing a whole bigger picture. And so same thing now is you've got to shrink the size down, the rate has to increase.
so you're talking about it was like change of the percentage, like you compare to the whole distance, like that. And that's why you say that's when they're getting closer, the rate of change is increase.
That wasn't part of this problem, but
But
just kind of enlarging it.
Yeah, I mean, this number gonna change or not? It's 192.
The 192, that's specifically at this point. So that's the rate of change at these 2 points, the 180 and the 225. That's like the radar gun. Okay. Instantaneous rate of change at this particular point for those legs of the triangle. If I make the legs of the triangle smaller, the rate of change is now going to be increasing. All right. Enjoy the spring break. This is all of chapter 3. So if you need to play catch up, hopefully not, you're not there. Hopefully you're automatically caught up on tasks and everything, right? But if you do need to, use your time wisely, right, to get caught up. Test will be on the Wednesday when we come back, so on the Monday, it's nothing but review. Put it all together. Pretty much at this very last point in the chapter, everything is all together anyway, so. 11 sections, but it's not necessarily all 11 individual things to be tested on.
You don't need questions.
That's probably not 20. I think I would like to do about 200, but I know you all probably shoot it. All right, enjoy y'all spring break. Stay safe if you're going on vacation anywhere. I heard don't go to Mexico. Morning spring breakers, not to go. I'm going to Denver. Oh, that's fun.
It's not right. So you say there's something go to a direction with a constant velocity, right? And that was the other, whatever it is, it's go to with constant velocity, and that they are different. So the distance between them is, it should be changing in a constant rate, and no? Why? No, no. That's going at a specific rate, but this right here, as you're shrinking the distances right here, it has to keep up. So in order to keep up with these constant rates, this rate is going to shrink and increase actually. As the distance shrinks, the rate is going to increase. Blowing up that balloon, just think about it. Blowing up that balloon, when it's this big, if you still put in a lot of air, the change of that balloon, the shape, size of that balloon change a whole lot, even though a lot of air went in, it went like that now. But at the very beginning, you blow into that balloon that same rate, it's going to go real fast. This is just the opposite. You have a bigger picture, and now you're taking out, as I'm taking out the same amount of rate, that balloon is going to start slowly, and all of a sudden, fast. Okay. Take some numbers for those two sides. Leave it right there. And you'll see it. Yes, to the date of the test. Yes. Somebody, Monday. When we do it, I don't have anything recorded just yet. So on Monday, I'll post what we do in Friday.
Because that's prior to. Where it's affecting, do you think linear measure is affecting the volume and area? Right? But even though it's not proportional. When it might be proportional in the linear thing, but then you put square and everything, we can. Okay. Very good.